So let's look at how we can use Leslie matrices to make our lives easier, to look at long-term population modelling. Now, there's a pattern when calculating population matrices, as you've noticed by the previous video. P1 is equal to L times P0, or our population at the end of time period 1 is our Leslie matrix times by the initial population matrix. Population at the end of period 2 is our Leslie matrix times by our population at the end of period 1. That's the same, though, as saying our Leslie matrix squared times by our initial population. Okay? Because all we're doing, instead of doing this, we're going L times LP0. All right? So we can find a population matrix PK, so where K is the time period, or what time period we're looking at, using the formula that PK is going to be our Leslie matrix to the power of K times by initial population. So the general form of a Leslie matrix, which we've already talked about, is constructed by assigning fecundity rates across the top row, survival rates along the sub-diagonal beginning under F1, and zeros in all other elements. So you can see that Leslie matrix in the blue box here. N is the number of age groups being considered. S is our survival rate. So from going from age group X to age group X plus 1, remembering that your survival rate for the very last group is 0. Our fecundity rate, now in the Cambridge textbook, they refer to that as the birth rate, so it's B instead of F, but the fecundity rate is the average number of female offsprings from a mother, okay, in age group X during one time period. And the population matrix is an n by 1 matrix representing the size of each age group after the kth time period. So let's look at some examples using that. A particular species of mouse is known to have a maximum lifespan of 3 years. The initial mouse population is given by, and the Leslie matrix is given by. Determine the approximate female population after 1 year. So that is going to be equal to our Leslie matrix times by our initial population. So 0.5, 2.1, 0.3, 0.6, 0, 0.40 times by 16, 25, 14. Going to your calculator, you get approximately 65, 10, and 10. So 65 plus 10 plus 10 is 85. So therefore, the total number of female, it did only ask female, mice after 1 year is 85 mice. Next one, calculate the total population. So that means I'm going to have to include the males as well. After 5 years. Identify any assumptions you make and comment on the effects of these assumptions in your answers. Now I want the population after 5 years. So I want N5. So that's going to be my Leslie matrix to the power of 5 times N0. So 0.5, 2.1, 0.3, 0.6, 0, 0.40 times 16, 25, 14, and I forgot my power of 5 there. Go to your calculators and you get approximately 208, 78, and 27. So 208 plus 78 plus 27 equals 313 females. So 313 times 2 equals 626. Therefore, there would be 626 mice after 5 years. Now, this question also asked us about our assumptions, and they are very important. So, equal numbers of males and females, or you could say male and female proportions are the same. Same thing. We are also assuming that our survival and fecundity rates remain constant over that 5-year period. Now, another thing, if you look at what we ended up with, those younger mice are growing rapidly. So our younger mice are growing rapidly. So for that to occur, our survival rate of our 1-year-old or 1-year-olds may decrease depending on resources. Oops. So there might be too many to sustain regarding food, for example.